The first topic that I'm going to report is about other fire mitigating methods. So, when water damage poses almost as much of a threat to a structure or its contents as does fire, a variety of other fire mitigating methods are available. The first one is halogenated hydrocarbons, known commonly as halons. These are gases stored as liquids in which one or more hydrogen atoms have been replaced by halogen atoms. Although the original hydrocarbons are often highly flammable gases, the substitution of halogen not only makes the gas itself non-flammable, but also gives it a flame extinguishing capability by interrupting the chemical chain reaction in a fire. Until the mid-1990s, the most widely used of these compounds was halon 1301. The name signifies that its molecules contain one carbon atom, three fluorine atoms, no chlorine atoms, and one bromine atom. The advantages of halon 1301 and other halons are that it can be released with relative safety through a flooding system into areas such as computer server rooms, quickly extinguishing a fire with little harm to the contents. No oxygen displacement to threaten life support, little demonstrated harm to people, and no residue left on electronic components. It, it is also lightweight and space-saving. Until the late 20th century, Halon 1301 was used on all commercial aircraft and in many special building applications. However, was subsequently identified as a long-lived significant threat to the Earth's protective stratospheric ozone layer. Its production was thus phased out as of 1994. Next is foams. Foams, or masses of gas-filled bubbles, are lighter than water and flammable liquids. They float on the surface of a burning liquid, smothering and cooling the fire and sealing in vapors. Foams can be designed to inundate a surface or to fill cavities. They can be thin and rapidly spread or thick, tough, and heat resistant. Some foams can be spread by foam water sprinkler system. Many foaming agents suited for various purposes are available. Another example is carbon dioxide. Among other inerting gases, CO2 has long been used to prevent ignition of potentially flammable mixtures and extinguish fires involving flammable liquids or gases. Because of its oxygen displacement, CO2 is often used in tightly confined spaces that are free of people or animals. For example, display cases, mechanical or electrical chases, and unventilated areas above suspended ceilings or below raised floors. It also finds application in data centers, telecommunications equipment, and electrical equipment rooms. In short, wherever water damage is a major concern. CO2 is a non-combustible and will not react with most substances. It does not conduct electricity and will not normally damage sensitive electronic equipment. There is no residual cleanup associated with its use as a fire suppressing agent. Next is clean agent gases. So it works in a manner similar to that of halons but with zero ozone depletion potential, with a much shorter atmospheric lifetime than halons. It is also less threatening as a greenhouse gas contributing to global warming. It will typically require about 50% more cylinders than halon 1301 for the same hazard. One example of clean agent gases is FM200. It is a clean, non-toxic, odorless, electrically non-conductive suppression agent consisting of carbon, fluorine, and hydrogen. It is stored in pressurized steel containers and when released vaporizes and interrupts the combustion process by mixing with the air. Upon actuation, it leaves no residue. Next is portable fire extinguishers. Most fires in buildings can be extinguished at an early stage with these commonly seen devices. Portable fire extinguishers are rated or classified based on the type of fire they are designed to fight. How many extinguishers are required and where they are located depend upon the hazard of the occupancy. The following material is a short summary of NFPA 10, standard for portable fire extinguishers. Portable fire extinguishers are labeled as follows. So we have here Class 1A to 40A. So these extinguishers are used on Class A fires involving ordinary combustibles such as wood, cloth, paper, rubber, and many plastics, and effectively suppressed by the heat-absorbing cooling effects of water, the coating effects of dry chemicals, or the interruption of the combustion chain reaction provided by dry chemicals. Next is Class 5B to 40B. These extinguishers are used on Class B fires involving flammable or combustible liquids, flammable gases, greases, and similar materials that are best suppressed by excluding oxygen, by inhibiting the release of combustible vapors, or by interrupting the combustion chain reaction. Next is Class C. Class C fires involves energized electrical equipment. The extinguisher contents are non-electrically conducting, such as CO2 or dry chemicals. Another one is a Class A, B, C, or the multi-purpose dry chemical extinguishers filled primarily with ammonium phosphate and suitable for use with all three classes of fire. Unfortunately, ammonium phosphate has the disadvantage of leaving an especially hard residue unless promptly and thoroughly cleaned as soon as a fire is extinguished. Next is Class D. Class D fires involve combustible metals or metal alloys. The extinguisher contains dry powders such as copper or graphite compounds or sodium chloride. These extinguishers are used on a variety of combustible metals. The specific combustible metals for which the extinguisher is intended is printed on the extinguisher's nameplate. Next is Class K. Class K fires involve cooking appliances that have vegetable oils and animal oils and fats, such as those found in commercial kitchens, restaurants, and cafeterias. These extinguishers contain a potassium acetate-based low pH agent that discharges as a fine mist to help prevent fires from grease splashes while the appliance cools. Next topic is about lightning protection. Lightning is nature's most destructive force. The average lightning discharge is estimated at 200 million volts, 30,000 amperes, and courses through a grounded object in less than a thousandth of a second. Cold lightning bolts have ample current, voltage, and duration to shatter and kill, but not to ignite combustibles, while hot bolts will ignite combustibles. Lightning protection can protect not just a building itself, but also serve to protect a building's electrical distribution system. The decision on whether to protect a structure against lightning depends upon an evaluation of these factors. 1. Frequency and severity of thunderstorms. 2. Value and nature of building and contents. 3. Hazard to building occupants. 4. Building exposure. 5. Indirect effects. First example of lightning protection is Franklin cone. A Franklin cone, named for Ben Franklin, is simply a mast with a conductor running straight to ground. A cone of protection is formed that protects the objects within it from strikes by absorbing the lightning stroke at the mast and grounding it harmlessly. The closer an object to the ground and the mast, the better the protection. So buildings within an interior solid angle of 60 degrees get excellent protection, and those within an angle of 90 degrees get good protection, and those within an angle of up to 126 degrees get fair protection. Next example is the overhead ground shield wire. Forming a continuous earth terminal, this shield is linear and horizontal, so the protective volume is a triangular prism rather than a cone. This is most commonly used to protect overhead transmission lines. It is recommended that both the single mast and the overhead ground shield project above any structure within the protected zone by at least 6 feet, and more height is better. Third example is the Faraday cage, named for Michael Faraday. This approach depends upon an open, interconnected mesh covering a large, non-conducting mass or the building to draw a lightning stroke and conduct it to earth. This leaves large areas of the roof exposed, so the higher the air terminals and the denser the mesh, the better the protection. All metallic objects on the roof should be bonded to a looped conductor that joins the air terminals. These air terminals commonly are placed both at roof edges and ridges at intervals of about 20 feet. The conductors usually are made of copper and are best housed in a plastic pipe conduit. Ground conductors, often called counterpoise conductors, are also installed to connect the air terminals. This is a diagram of a typical lightning protection system. So, air terminals are commonly found at the roof edges, and if the building has a steel column, it can serve as a down conductor that connects the air terminals and the ground plate. Fourth example is the lightning arresters. A lightning arrestor is a special type of surge arrestor, generally connected at one end to an overhead electrical line and at the other end to the ground. It thus suppresses any lightning voltage surges that appear in the electrical line so that the equipment downstream on that line is not damaged. A lightning arrestor operates only when it senses a voltage surge. At that point, it conducts the surge to the ground through its own low resistance and partially dissipates the energy of the surge in the body of the arrestor. Once the surge has passed, the arrestor returns to its high impedance quiescent state, presenting an open circuit connection to the normal voltage line to which it is connected. Last example is the high-rise buildings. Lightning protection systems are particularly important for very tall buildings. Figure 25.33 shows the schematic diagram for the John Hancock Center in Chicago, a structural steel building of unusual height. Intermediate loops at the mechanical equipment floors help to overcome the problem posed by the poorer conductivity of metal piping systems, which can become relatively high impedance spots for lightning, with resultant destructive effects. The intermediate loops are connected to each outside column as well as to the main electrical, plumbing, air conditioning, and fire protection risers. These loops are also connected to both the roof conductor and the ground counterpoise conductor. Next topic is about fire alarm systems. So fire alarm system serves primarily to protect life and secondarily to prevent property loss. Because buildings vary in occupancy, flammability, type of construction, and value, a fire alarm system must be tailored to the needs of a specific facility. In schools, for instance, where the paramount consideration is rapid, orderly evacuation, the same general type of system will be used from project to project, although the means of automatic detection will vary with construction type, building height, specific area use, furnishings, and stuffing. The fire alarm is part of the overall fire protection system of a building. In particular, it overlaps with the design of safe egress and smoke or fire control in matters such as fan control and smoke venting, smoke doors, smoke door closers, rolling shutters, elevator capture, and the like. These automatic functions are initiated by operation of the alarm system but are designed in accordance with the overall fire protection plan. Like other alarm systems, a fire alarm system has three basic parts: signal initiation, signal processing, and alarm indication, so as shown in the figure. The signal initiation can be manual, like pull stations or telephones, or automatic, like fire and smoke detectors and water flow switches. The alarm signal is processed by some sort of control equipment. Sa figure, amo na siya ang control panel, which in turn activates audible and visible alarms and in some cases alerts a central fire station or municipal authorities. The last topic is about fire codes, authorities, and standards. NFPA codes, they are actually standards awaiting legislative adoption into codes, are published by the National Fire Protection Association. They bear directly on fire alarm systems arrangement. And there are probably more codes and standards in the area of fire protection than in any other area, with the possible exception of structural design. Although the following documents are devoted primarily to fire protection and life safety, they also govern the type of fire alarm system to be installed, its components, and its installation. We have here listed are the NFPA codes, and the authorities includes ANSI or American National Standards Institute. And this organization does not develop standards. It accredits standards that are prepared by professional and technical societies and associations. Approval and listing by ANSI validates an organization's standards development process. Next is the ICC, or the International Code Council. Publishes the International Fire Code, a unified code that has generally supplanted legacy regional codes in the United States. Another one is the HUD, or the Department of Housing and Urban Development. Publishes requirements for residential buildings and care type facilities. FHA minimum property standards are included here. Next is the UL, or Underwriters Laboratories. Numerous performance standards are published by Underwriters Laboratories. UL laboratories test equipment for inherent safety and for performance according to the manufacturer's specification. A product is listed if the equipment passes UL safety and performance test. Some UL standards related to fire protections include, so listed here are UL detection standards. Next is UL alarm standards. In addition, all codes and standards undergo a cyclical updating process, with new versions appearing on a regular basis. The specific recommendations given in the following sections are representative of good practice. Actual design must be based upon and must meet the requirements of current NFPA standards, plus all codes having jurisdiction in the particular locale of a project. That's all, and thank you for listening.